Hello, I'm Davis Binger, and let's talk about projectile motion. Today we will look at problem 4 from the 12.7 handout. We consider a potato cannon, which fires a potato from a height of 3 feet with an initial position of 003, an initial velocity of 20, 40, 90, and a crosswind producing acceleration of 5 feet per second in the northeast direction. Implicit to this problem is that we have an additional acceleration vector due to gravity in the downward direction of 32 feet per second squared. We are asked to determine the maximum height of the potato and the time of flight. We will assume that north-south is in the first coordinate, east-west, the second coordinate, and the third coordinate up-down, with the first of these being the positive direction. Alright, in problems of this type, your approach is to find the acceleration function, then take antiderivatives to find a position function and a velocity function. And once you have these functions, you can then answer the questions. In our case, we have an acceleration due to gravity and an acceleration due to a crosswind. Let's start with discussing this acceleration due to the crosswind. We know that it has a magnitude of 5 feet per second, and we are told it is in the northeast direction. Now the northeast direction is equal parts vertical coordinate, equal parts north-south coordinate and east-west coordinate. And we've assigned east and north to be positive, so this is in the 1, 1 direction. You can find a unit vector in this direction to be square root of 2 over 2, square root of 2 over 2, comma 0. And after multiplying by 5, you come up with an acceleration vector associated to this wind of 5 square root of 2 over 2, 5 square root of 2 over 2, comma 0. Again, we have the acceleration due to gravity, which is negative 32 feet per second squared in the downward direction, which is a vector of 0, 0, negative 32. And we sum these two acceleration vectors to find the acceleration vector for our potato. All right. Now, we take an antiderivative to find the velocity function, and this is just done by taking the antiderivative coordinate by coordinate. These are all constant functions, so their antiderivatives will all be linear functions. In this case, the first coordinate is 5 root 2 over 2t plus c1. The other coordinates you can find similarly. Now, this antiderivative we've taken is a family of antiderivatives, depending on the parameters c1, c2, and c3. We are interested in finding a single velocity vector associated to this situation at hand. Now, our choice of a velocity function depends on our initial velocity. We evaluate this antiderivative, this family of antiderivatives, at 0 and equate them with our initial velocity and solve for c1, c2, and c3. In this case, by evaluating velocity at 0 and setting it equal to 20, 40, 90, we find that c1, c2, c3 is equal to 20, 40, 90. Now it is a common trap to think that these constants will always be equal to initial velocity. And this is often the case when we're dealing with parabolic motion or body, like acceleration of a projectile object. But it is not always the case. I encourage you to be careful and really understand this point. You find the c1, c2, c3 by evaluating the velocity function at 0 and equating that with your initial velocity. It's just that when you evaluate each of these linear functions at 0, it is 5 root 2 over 2 times 0 plus c1, which is exactly c1. So evaluate the v of 0 is exactly c1, c2, c3. So that's why you get c1, c2, c3 is equal to 20, 40, 90, not because 20, 40, 90 is the initial velocity. Okay, with this bit of information, we have the specific velocity function associated to our situation, and with this specific velocity function, we can then take a second antiderivative to find the position function. Now here's our velocity function rewritten. We take an antiderivative of each coordinate, much the way we did previously, and our linear functions have antiderivatives which are quadratics, and the first coordinate is 5 root 2 over 4 t squared plus 20t plus k1, and the other coordinates you can find similarly. Now again, after taking an antiderivative, we have a family of antiderivatives depending on the constants k1, k2, and k3. We will find these k1, k2, and k3 by using the initial position of the potato, which we have taken to be 0, 0, 3. Now, we evaluate r at 0, 0, 3 and set each coordinate, or set this function equal to 0, 0, 3, and we find that k1, k2, k3 is equal to 0, 0, 3. So our position function is equal to the following. Now, we found the velocity function, we found the position function. We can turn now to answer the questions that they posed to us. Recall that the two questions they asked were, what is the maximum height of this object, and what is the time of flight? Let's start with answering the question about the maximum height. The maximum height is found when the z-coordinate of the position function obtains its maximum value. Recall the theory from Calculus 1. A function obtains its maximum value when its derivative has a 0. And we know it's a maximum if its second derivative is negative. We are told that we have acceleration due to gravity of negative 32 feet per second squared. So the second derivative of the third coordinate is negative. So a maximum will occur when the first derivative is equal to 0. So we will solve the equation negative 32t plus 90 is equal to 0. And this is 90 equals 32t, or t equals 45 over 16. Evaluating position at this point gives us a value of 129.5625, and this is our max height. Time of flight. Time of flight will begin at 0 and end when we have returned to Earth. This amounts to calculating the zeros of the position function. So a simple application of the quadratic formula to the z-coordinate of our position function will give us the time when our potato hits the ground. In this case, our time of flight is given by 45 plus root 207.3 divided by 16. Alright, thank you guys for watching, and have a good evening.